There is a machine so familiar that most people have stopped thinking about what it actually is. They know what it looks like. They know what it did. Very few have considered how it worked, and fewer still have asked why it worked so consistently. The guillotine was not simply an instrument of death, and it was a precision mechanism, one whose reliability depended on deliberate decisions about weight, geometry, and the controlled use of gravity. Every component had a specific mechanical function. Every decision, the weight of the blade, the angle of the cut, the tolerance of the guide channels, was made to solve a specific problem. This episode is about those decisions, and about the engineering logic behind a machine that governments used for nearly 2 centuries, and about what that logic reveals. Here is the question at the center of this episode. Of all the mechanical components in a guillotine, the blade, the frame, the rope, the release, which single element was most responsible for making the outcome certain rather than merely probable? We will come back to that. Before the guillotine, France executed by sword, by rope, by wheel. Each method had a different failure mode, and those failure modes mattered, not just to the condemned, but to the state that needed the procedure to project authority. Beheading by sword required a skilled executioner. Even in the most capable hands, it was not always clean. A sword is a human tool, dependent on strength, on timing, on the angle of the strike. Human variables are not constants. The institutional problem was not cruelty. The institutional problem was unpredictability. An execution that required multiple attempts undermined the legal theater it was meant to perform. Joseph Ignace Guillotine, the physician whose name the device inherited, did not design the machine. He proposed the principle that execution should be mechanical, instantaneous, and identical for every condemned person, regardless of their social rank. The actual engineering was delegated to Antoine Louis, Secretary of the Royal Academy of Surgery, who produced the technical specification in 1792. Louis was not a machine maker. He was a physician who understood mechanics well enough to write a specification that craftsmen could build from. His specification addressed a specific mechanical brief. Build a device that will sever the human neck in a single, uninterrupted stroke, with certainty, under all foreseeable operational conditions. That brief, certainty under all foreseeable conditions, is the key phrase. It is not asking for a device that usually works. It is asking for a device that always works. And always is a very different engineering target from usually. The difference between usually and always is the difference between a guess and a guarantee. And guarantees in mechanical systems come from one thing: understanding which variables you can control, and then controlling them. Louis was not designing from zero. Mechanized execution devices existed in Scotland, Germany, and Italy before the French guillotine. The Halifax gibbet, the German DL, the Italian mania, all used a falling weighted blade to sever the neck. These devices existed for generations before Louis's commission. They sometimes worked. The question Louis was tasked with answering was a harder one. Why did they sometimes fail? And how could those failures be eliminated? The failure modes of earlier devices were well understood by anyone who had observed them. A blade that was too light could slow significantly before completing its stroke. A blade that was poorly guided could deflect. A release mechanism that was imprecise could give the blade an unintended lateral impulse at the start of its drop. Each of these failure modes had a mechanical cause, and each mechanical cause had a mechanical solution. The engineering challenge was not to invent something new. It was to analyze what had gone wrong before and specify a system that removed each failure mode systematically. Louis's contribution was not mechanical innovation in the modern sense. It was mechanical clarity, a written specification that identified the critical variables and set requirements for each one. And the craftsman who built the first device worked from that specification. The result was a device first used in April 1792. Contemporary accounts describe the outcome as completing in a single stroke. That was not luck. It was the consequence of solving the right engineering problems in the right order. Let us begin with the blade itself. Not with its symbolism, with its mass. The guillotine blade assembly was not designed to be as heavy as possible. It was designed to be heavy enough, which is a fundamentally different requirement. The physics are straightforward. A falling mass acquires kinetic energy in proportion to its weight and the height from which it falls. And the kinetic energy delivered at impact determines whether the blade completes its stroke through the full diameter of the neck. The target of the cut is not homogeneous material. Bone, cartilage, muscle, and vascular tissue each resist differently. A blade that has enough energy for the softest case, but not the hardest, will fail in exactly the circumstances where failure is most visible. Lewis's specification established a blade assembly weight, blade, spine, and hardware combined, that would deliver reliable kinetic energy for the worst-case anatomical scenario, not the average one. The margin of excess was intentional. This is the engineering concept of a safety factor. You do not specify for what usually happens. You specify for what can happen, and with enough margin that degradation in other components does not push the whole system below its minimum. The blade's weight also served a second function. It stabilized the blade's path during the drop. A heavier moving object is less affected by small lateral forces, from guide friction, from air resistance, from any slight imperfection in the release, than a lighter one. The mass provided not just energy, but mechanical stability. The drop height was chosen to complement the blade weight. For a given required kinetic energy at contact, drop height and mass are mathematically exchangeable. The guillotine settled on approximately 2 meters of drop, which balanced energy requirements against the practical constraints of transporting a structure that needed to be erected in a public space. Together, blade mass and drop height produced a reliable kinetic energy figure. But kinetic energy alone is not the full story. How that energy is delivered, and in which direction, is at least as important as how much of it there is. Most people who know anything about the guillotine's design know about the angled blade. The oblique cut, at approximately 45 degrees to the horizontal, is its most visually distinctive feature, but it is commonly misunderstood. The common explanation is that the angled blade reduces resistance, and that is partially correct, but it misses the more important engineering function. A flat horizontal blade must exert cutting force across the full diameter of the neck simultaneously. The resistance peaks at the moment the blade contacts bone, and all of that resistance is concentrated in a single instant. An oblique blade makes a progressive cut. It contacts the neck at its leading edge first and draws the cut across the diameter as it falls. This does two things. It distributes the resistance over a longer time window, and it creates a shearing component of force in addition to the compressive component. Shearing force is more efficient at cutting than pure compression. And you see the same principle in a sharp knife drawn across material versus pressed straight down. The drawing action concentrates force at a moving contact point rather than distributing it across the full width. The oblique blade also reduced the risk of deflection. A flat blade encountering off-center resistance had more rotational freedom. It could torque slightly within the guide channels. See, an oblique blade under the same conditions was constrained by the geometry of its own progressive contact to continue on its established path. This is the engineering insight that is almost always left out of descriptions of the guillotine. The blade's angle was not chosen because it looked more elegant, and it was chosen because it produced a mechanically more predictable stroke one that was less sensitive to variation in what it encountered. Now we come to the component that most people overlook entirely, and that is, in terms of the system's reliability, arguably the most important one. The guide rails are two vertical channels, one on each side of the frame, that the blade spine fits into. And they look like infrastructure, like the boring structural part of the machine. They are not. Here is what the guide rails actually do. When you release a weight to fall vertically, it does not fall in a perfectly straight line unless something forces it to. Air currents deflect it. Asymmetries in the release mechanism give it a slight lateral impulse. A friction at one contact point and not another creates a torque. Without the guide rails, the blade would not follow a straight vertical path. It would follow a path determined by every small perturbation in the system, and those perturbations would vary unpredictably from one use to the next. The guide rails eliminate this problem by removing the lateral degree of freedom entirely, and they constrain the blade to move in exactly one direction, straight down. Not approximately straight down. Straight down. This sounds simple. It is not. For the rails to work correctly, the tolerances, the gap between the blade spine and the channel face, must be within a specific range. Too tight, and the blade binds, on adding unpredictable friction that can slow or stop it. Too loose, and the blade has enough lateral freedom to deflect. Lewis's specification addressed the guide rail tolerances explicitly, not as a single value, but as a range, acknowledging that the mechanism needed to function across temperature variation, lubrication conditions, and accumulated wear. A range, rather than a single value, is the mark of engineering maturity in a specification. Here is the answer to the question we opened with, the one about which component was most responsible for the machine's certainty. The blade weight provided the energy. The blade angle provided the efficiency. But the guide rails provided the determinism. They are what transformed a falling weight into a reliable mechanism. The release mechanism, the system that held the blade at height and then freed it, was a component that received less attention than the blade in Lewis's original specification. It would eventually become a focus of post-operational refinement. Early versions used a rope and pin system. The blade assembly was raised by rope and pulley to the required height. A pin held it there. Pulling the rope released the pin, and the blade began its drop. The problem with the early system was consistency of release. If the operator applied any horizontal force to the release rope as they pulled it, that force was transmitted through the mechanism and could give the blade a slight lateral impulse at the start of the drop. A lateral impulse at the top of a 2-meter drop means a small angle of deviation. But 2 meters is long enough that a small angle produces a measurable lateral displacement at the point of contact. This is the kind of failure mode that is easy to overlook in testing and visible only in operation. And later trigger designs addressed this by introducing a mechanical linkage between the release pull and the pin. The operator's force was now applied to a trigger that rotated on a pivot, pushing the pin in a direction orthogonal to the blade's path. The release force could not be transmitted as a lateral impulse to the blade. This is a small engineering refinement. But it is exactly the kind of refinement that distinguishes a machine that usually works from one that always works. The operator's force was redirected, turned from a potential source of error into a clean path orthogonal input. Any mechanism with moving parts and contact surfaces must address friction. In the Guillotine, the primary friction surface was the interface between the blade spine and the guide rail channel faces. Guide rail friction had two effects. First, it slowed the blade, reducing kinetic energy at contact. Second, it was variable. Dirtier rails produced different friction on different days. Variability in friction meant variability in delivered force. Lubrication was the primary management strategy. Period accounts and technical literature consistent with the era document the use of tallow, rendered animal fat, as a lubricant on the guide rail contact faces. Tallow provided a consistent friction coefficient and was replaced on a scheduled basis. The blade was also cleaned after each use, not only for the obvious reasons, but because accumulated material on the blade spine would alter its fit in the guide channels, effectively changing the tolerance and therefore the friction. This maintenance discipline, consistent lubrication, consistent cleaning, consistent inspection of the rail faces for wear and burrs, was itself part of the engineering system. The mechanism's performance was a function not just of how it was built, but of how it was maintained between uses. The wooden frame of the guillotine is often treated as structural background, the thing that holds the important parts. But the frame is itself a precisely specified component. The frame had to be rigid enough that it did not flex under the dynamic load of the blade assembly dropping. And any flex in the uprights would transmit lateral movement to the guide channels, which would transmit it to the blade. The frame's rigidity was part of the guide rail's precision. The height of the frame was not arbitrary either. It needed to accommodate the full drop distance plus clearance below the cutting point, and to do so at a height that allowed the mechanism to be transported, erected, and disassembled on a regular basis. The frame also anchored the guide rails. The precision of the rails was only as good as the precision of their mounting. Lewis's specification included the rail mounting geometry, specifying that the rails must be parallel and vertical, not merely approximately so. When you look at the guillotine's engineering as a whole, blade weight, blade angle, guide rails, release mechanism, lubrication protocol, frame rigidity, you are looking at something recognizable to any modern engineer: a system. Each component was specified in relation to the others. The blade weight was specified given the drop height. The drop height was specified given the rail length, and the rail tolerance was specified given the expected range of lubrication conditions and wear rates. Change one, and the correct values of the others change. Antoine Louis was not using 20th century systems engineering language, but the logic of his specification was systems logic. Identify the required output. Identify the variables that affect it. Specify each variable to a range that guarantees the output, and account for the interactions between variables. This is historically significant. Systems thinking in engineering is usually described as a development of the 20th century. The guillotine specification suggests that the practical logic of it was available to thoughtful engineers much earlier when a problem required it. And the design was also documented in transferable form. Any competent craftsman with the right materials could build a device to the specification and know that it would perform as intended. The documentation was part of the engineering. The revolutionary state made a specific claim when it adopted the guillotine, that execution was an administrative act. It's not a spectacle, not a punishment in the old sense. A legal procedure executed by a machine on behalf of the law. For that claim to be credible, the machine had to perform. A mechanism that failed visibly would have contradicted the institutional argument the state was making. The engineering precision of the guillotine was therefore not just a technical achievement. See, it was a political requirement. The certainty of the mechanical outcome was the material expression of the certainty of the legal outcome. The machine had to work without hesitation, because the law, in theory, did not hesitate. See, Michel Foucault argued that modern state power shifted from spectacular punishment to administrative punishment, from the public display of physical suffering to the quiet efficiency of institutional procedure. The guillotine sits precisely at that transition. The guide rails in this reading are not simply mechanical components, and they are a statement about the relationship between the state and the act it was performing. We have removed the human variable. We have made this a matter of physics, not judgment. The machine decides nothing. It only executes what has already been decided. The guillotine remained France's official execution method until the abolition of capital punishment in 1981, and the last execution was in 1977. For 185 years, the essential design remained unchanged in its fundamental parameters. That persistence is itself an engineering data point. When a design survives for nearly 2 centuries without fundamental modification, it means one of two things. Either the design was optimal from the beginning, or the institutional context prevented improvement. In this case, the evidence supports the first interpretation. The post-Lewis modifications that were made, improved trigger mechanisms, better lubrication schedules, refinements to rail mounting, were all peripheral to the core specification. The blade weight, the angle, the guide rail principle. These were correct from the start. This is what makes the guillotine unusual as a machine. It was specified correctly the first time, in a domain where the cost of iterative refinement was high, and the first working version had to be close to the best one. The guillotine is often used as a symbol of the terror, of egalitarian death, of revolutionary justice. All of those interpretations are legitimate, but they tend to obscure what the object actually is at the level of mechanism. At the level of mechanism, it is a gravity drive-constrained linear actuator with a weighted oblique-edged tool. It was designed to convert gravitational potential energy into a precise linear force applied at a specific point. Every major design decision serves that conversion, and the guide rails constrain the path. The blade weight provides the energy margin. The oblique angle concentrates the force. The release mechanism introduces the falling mass without introducing its own forces. The frame holds the geometry true. Each component does exactly one job. And what the engineering reveals is not a story about death. It is a story about problem solving, about how engineers, without modern vocabulary or computer simulation, identified the critical variables in a complex mechanical problem and controlled them. They used systems thinking before that term existed. They specified tolerances before precision manufacturing was common. But they documented their reasoning in transferable form. The result worked the first time and kept working for nearly 2 centuries. Some machines reward analysis. This is one of them. Not because of what it did, but because of how carefully someone thought through what they needed it to do.